For those that just joined, we will get started here soon. Thank you again for joining the webinar. I'm just going to allow like maybe one more minute. So we'll start 1 minute after the hour, just to allow a few more people to jump on. Thanks for your patience. Alrighty, we're going to get started. Hello, I am Kirsten Weplow, and I will be your moderator today. On behalf of the whole Wärtsilä Energy Storage and Optimization team, I'd like to welcome you to our webinar, Advancing Energy Storage Innovation to Meet Evolving Industry Needs. Thanks for joining us. Our speakers today will provide a wide range of energy storage expertise, covering the life cycle of the systems from design and development through to operation. Alicia Lockhart of our Lifecycle Sales and Offer Management team will kick us off with a short introduction to Wärtsilä Energy Storage and Optimization. Then Neha Sinha with hardware will delve into how to consider cost and operational performance when it comes to the best design. Shah with our software product management will then dive into how to maximize the amount of usable energy during BESS operations with sophisticated software. And lastly, Alicia will come back and discuss how to maximize system performance throughout its lifespan. Please make sure to utilize the Q&A chat box for all questions. With that, I will kick it off to Alicia.
Thanks, Kirsten. So on behalf of all my speakers and fellow panelists here, thanks again for joining us. And we just wanted to do a brief introduction to Wärtsilä and give you an idea about our global footprint here. So we are incredibly proud to be considered one of the top 3 energy storage integrators globally, with over 6.5 gigawatt, 12.5 gigawatt hour of systems either awarded contract or currently in deployment. With our 15-year track record of growth and industry leadership, we have successfully delivered over 125 projects around the world, and we look forward to talking more about this with you today.
Hey everyone, so my name is Neha Sinha. I'm the product manager for our hardware systems, and I want to talk about how we consider cost and operational performance in hardware design. So what you see on the screen now is the total cost of ownership of a BESS site. And I want to walk through each of these categories and talk a little bit about how we can influence cost in each of these categories when we're considering hardware design. So the first section is battery racks. This makes up majority or kind of the largest portion of the total cost. Batteries have historically been kind of that largest cost factor, but we do see battery costs coming down. And so what we can do is consider how to shorten the development cycle of integrating new higher capacity or higher performance cells into our systems. So you see that benefit as soon as possible. But really, as battery costs decrease, we see that these other categories here on the screen become more important. So the next 2 sections are equipment and EPC and BOP. I'm going to start at the top with equipment, and that is obviously the actual equipment that we design and deliver. So that includes your BESS enclosure, your inverters, and your electrical connections. When we talk about reducing costs, obviously reducing the cost of each of these components is a critical factor. But we also consider how to reduce the total number of units we need, because the fewer you have at site, the lower your total cost of equipment. For battery enclosures, that usually means increasing the capacity of each system. The higher capacity of one BESS enclosure, the fewer of them you need. And for inverters, it usually means right-sizing them appropriately so that they are most efficient and effectively connected to your BESS systems. I also want to talk a little bit about flexibility. This is, we just announced an AC block system as our new product line. And this is kind of a new unique form factor that gives you the opportunity to think about flexibility in a different way than we previously have with DC block systems. An AC block is when you have string inverters internalized inside of your enclosure, and it allows you to control each rack independently, which gives you the ability to structure your system in a very different way than you do with DC blocks. So alternative configurations like that are key when you're thinking about ways to keep your system flexible. And then EPC and BOP, this really falls in the scope of our EPC contractors, but of course we can influence the cost of that work by changing our hardware design. And one thing that I think is really interesting, and we've just really started the conversation on, is the opportunity as the industry matures to standardize electrical interfaces between equipment. So that's between the BESS and the inverter and between your aux power connections. And what this can do is by standardizing your interfaces, you can reduce the cost of those interface components, but you can also reduce the amount of unique site training that happens no matter what equipment you're installing at site. The next category is transportation. This has become an increasingly discussed element of the system because of this kind of conformity that we've seen in recent years toward a 20-foot enclosure footprint. And the reason why we want a containerized footprint is a standard ISO container that you can stack on ships, that you can put on trucks, standard container trucks, is significantly cheaper than a break bulk shipment or a custom footprint. So we can save costs with transportation that way, but I mentioned before, you can decrease the total number of units to save on equipment cost. But usually when you increase capacity within your system, those higher capacity battery modules come at a higher weight. And the higher weight of your module, the higher weight of your total system, we're really started to hit that upper limit on how heavy a containerized system can be and still be transported by ship, lifted at port, and put onto trucks and transported to site. And so when we consider transportation costs and minimizing that and optimizing it, we really have to consider on both sides. We want to get as much capacity in a system as possible, but not so much so that we can no longer transport using standard low-cost methods. And then here we also have locality of supply chain. As the energy storage market grows in different regions, the more we can diversify our supply chain and localize it to where our sites are located, the shorter distance this equipment has to travel. The next section is commissioning. So of course, in hardware design, our ability to influence commissioning, a lot of that comes from making components more accessible. So that can be anything from putting the switchgear at the bottom of the rack or just requiring no scaffolding to access it. Or it could mean ensuring that any of your testing and access points are accessible. And that's important for both commissioning and service, which falls under this last category of life cycle. We spent a lot of time talking about all of the other categories on this page, which are really the upfront costs, but life cycle is the 20 years or so that these battery sites are expected to be in operation. And so when we think about life cycle, we want to think about how to minimize service costs, maximize the amount of time your system is operational, and ensure that you are not taking away from the revenue that you expect this site to earn. So I've listed 3 categories here under life cycle, but I want to talk about them in more detail. So on the next slide, I've put them out so that we can dive deeper into each of these. And this is how we consider operation when we design BESS hardware. So the first category here is how we extend site lifespan. This means if your site is planned for 20 years, we want to make sure that all of the equipment is performing at the expected level throughout those 20 years. So the 3 things I have here start with high cycle life cells. The typical energy storage battery cell has a cycle life of about 10,000 plus cycles, and extending that can extend your battery and your system life. Design for longevity. By this, I mean, of course, ensuring that your equipment can make it throughout those 20 years, not just your batteries, but you're supporting thermal equipment and electrical equipment. And of course, the enclosure itself, ensuring that it is still operating and delivering the same level of IP and snow load and rain load that you expect it to be designed for over the course of its life. Augmentation is an ever widely discussed topic in this industry. It is when you add new battery cells or modules throughout the lifespan of your site to increase the capacity to accommodate for degradation. And it's really tricky because usually we're talking about 5+ years out from when the site is first installed to do the first augmentation. And the way this industry is evolving, we don't know what technology is going to be available in 5 years and how quickly battery technology will progress. We want our customers to be able to install the latest and greatest battery cells, but planning for that upfront can be really difficult. And so as much as we can future-proof our systems to be able to augment in the future, if that's part of the strategy of the site, the easier it is to expect that your site lifespan will last as long as it has been initially planned. The second category here is enhancing system availability. I just want to define availability very quickly. Availability is the amount of time that your site is online and operating at the design level of capacity. It's usually expressed as a percentage, and you're really trying to maximize how much availability you have in your site. So there are a couple ways we can do that with hardware design. The first is ensuring that you have reliable and repairable equipment. So you want to minimize downtime, ensuring that your equipment is durable and serviceable. The second are fire safety systems. Fire safety systems are incredibly important for a number of reasons. We want to make sure we keep people, first responders, safe, but we also want to make sure that our system uptime is maximized, and preventing fire safety events is critical to that. And then also recognizing that it's not just about preventing fires, but expecting that they may occur. And if they do, how do we contain those fire events? And that means limiting propagation of fire events and ensuring that no surrounding systems are impacted by one singular enclosure. And modular design, this is something that always comes up. The more modular design, the easier it is to come into a specific subsystem and easily repair or replace or upgrade your components. The final category here in operational considerations is optimizing system performance. So we can do this a couple ways. One is using those, I mentioned, technology's ever evolving, and we want to make sure we are using the latest and greatest cells. Usually that means the high capacity cells have high performance that you can then use to maximize the output of your system. Efficient thermal management. This is important for a few reasons. You want to make sure that you are minimizing degradation of your battery cells by ensuring that they are adequately cooled. But the other big consideration, chillers tend to be the highest consumer of auxiliary power in your BESS system. So by making your chiller system more efficient, you can reduce the amount of aux power consumption you have throughout the site lifespan. And of course, that means that you are maximizing then the revenue you can gain from your site. And then the last one here, string level control. I talked a little bit about AC block systems earlier, and this is specific to that kind of a configuration. But one of those flexibility opportunities I mentioned earlier is this granular level of control you get when you have string inverters. You're now talking about controlling your system at a rack level. And what that enables you to do, along with software, is increase the amount of energy throughput you get through your system and the operational efficiency of your system. So with that, I will hand it over to Ruchi to talk a little bit more about how software can help you maximize the output of your system.
Hi, everyone. Thank you so much for joining. My name is Ruchi, and I lead software product management here at Wärtsilä, and I'm going to be talking today about how to maximize your best performance and usable energy in operation. So let's talk a little bit about what is usable energy. So the amount of usable energy you have is essentially how much energy are you able to push out of your AC port, right? How much is available for either you to meet your PPA obligations or for you to bid into the market? And this is a question that I think is really important to our asset owners and to our traders who are trying to figure out how much energy they should be trading in the market. So the way that I think a lot of traders think about this problem is, so they think about, well, how much energy do I have available to bid in the market? And that is a function of your system's capacity, your system's state of health, the true state of charge of the battery, which, can be differentiated from the state of charge that's reported, right? That reported state of charge is not always the true state of charge of your battery. And it's also a function of cell imbalance. And these four things are interrelated, right? So what we see that traders will often do is that they'll take the system capacity and the reported state of charge, and from that, they'll create an estimate of the energy that will be available for bidding, which includes certain error bars. So they might estimate, they may say, based on the system capacity and the reported state of charge, this battery has 100 megawatt hours available for bidding, but we're going to create a 10% error bar and we're only going to bid in 90 megawatt hours because we don't know enough about the system state of health. We don't know the true state of charge. We don't know cell imbalance. So these error bars are there for a reason, but ideally we want to minimize how much, we have to how much error bar we have to create, right? So what we would ideally want is we want to have reduced cell imbalance, and we want to have a more accurate estimation of the true state of charge of the battery at any given time. So how do we do this? We need to move to the next slide. And the reason, so I want to back up and explain why this is a little complicated. With LFP batteries, understanding the true system capacity can be complex. And the reason for that is that the voltage curve is relatively flat between 20 to 90%. And that makes it very difficult to accurately determine the state of charge during not normal operation, right? Because state of charge is estimated based on, it's based on voltage. If your voltage curve is flat, it makes it challenging to understand what the true state of charge of the battery is. And if you continue to operate the battery between 20 to 90%, and you rarely go outside of those bounds, that state of charge estimation can start being increasingly inaccurate. And so when your state of charge estimate is incorrect, then your estimate of your energy available to bid becomes incorrect, right? So we want to continuously essentially allow our battery system to recalibrate the SOC, meaning we want it to be able to go outside of this 20 to 90% area so that the battery management system can provide a more accurate estimate of the state of charge. All right, cell imbalance. Cell imbalance is another problem we see, and it is a similar challenge to state of charge calibration. So what is cell imbalance? Cell balancing ensures that all battery cells in a string are at a similar state of charge. Why is this important? This is important because the string is limited by the cell at the lowest SOC, state of charge, while discharging, and it's limited by the cell with the highest state of charge while charging. So if you see that chart on the right-hand side of the screen, which is depicting imbalance before cell balancing. So you can see that cell 2 is already at 100%, while cell 1 is at 95%, cell 3 is at 90%, and cell 4 is at 92%. So the other cells still have energy available. However, because cell 2 has already gotten to 100%, the energy in those other cells is effectively stranded. They cannot be accessed. And this is what happens when you have cell imbalance. You have stranded energy that you can no longer use to make money with your battery. So that means your system is not getting the maximum capacity out of your battery cells, and it means you have less energy available for bidding, which means in turn that you're going to make less revenue. So how do you solve for cell imbalance? Well, this varies by cell, cell type, but it typically involves resting at a specified state of charge. And once again, that state of charge is going to be outside of the flat area of the voltage curve. So you're going to be resting typically either below 20% or in an area above 90% where the voltage curve is steeper, which enables your battery management system to see the voltage differences between cells and to then adequately start balancing those cells. So we want to help our customers enable SOC calibration, state of charge calibration, and cell balancing with automation. So one of the challenges that we have here is that in normal operation, you typically do want to operate your batteries between 20 to 90%, right? You want to be able to have energy in the tank to discharge your batteries as needed and also to charge your batteries as needed to support ancillary service events. So most of our customers typically would prefer to keep their batteries in that range between 20 to 90%. However, in order to maximize usable energy, we need to ensure that the batteries are moving out of that range, on a regular cadence. Probably every couple weeks is, a good amount of time to be regularly ensuring that your cells are staying balanced and your state of charge is calibrated. So, some providers recommend that you pull the whole system out of market in order to balance the cells and to calibrate the state of charge. But we understand that our customers really don't want to do that. They want to retain the availability. They want to retain the ability to stay in the market. So we've created an automation that enables an individual inverter and its associated strings to undergo state of charge calibration and cell balancing. So that individual inverter will be taken to whatever state of charge is required based on the cell type, and then it will be available to rest for the given resting period. That inverter would still be available when called upon to meet market obligations. And meanwhile, the rest of your system is all staying within that 20 to 90%. And so you're able to stay in market, not pull the system out of market, continue to make money while ensuring that you maintain the usable energy of your system. So that's one way that we ensure, high usable energy for our customers. And now Alicia Lockhart will be speaking again to talk a little bit more about maximizing system performance.
Thanks, Ruchi. So at the beginning of the webinar, we looked at our global map where we could really see the breadth of our installed sites around the world. But I wanted to focus here a bit on the US for this specific webinar, where we have 2.5 gigawatt and almost over 8 gigawatt hours of projects installed within the US. Now, no matter what our contractual obligations are with these customers, where we have long-term service agreements or not, our goal as our customer's partner is to ensure that the system is reliable, efficient, and its performance is maximized. We can accomplish this by reducing system downtime and always advancing and innovating on our product design and iteration. So if we first start with reducing system downtime, this can take a lot of different forms. And one that's almost the most obvious is just effective and efficient maintenance planning. So while we're performing our maintenance, we're ensuring that we're maximizing the available power while we're on site doing that work. So only taking the equipment down that we're working on and then moving forward in a cadence where that equipment now comes online as we move through our maintenance plan. So this allows the customer to still have access to majority of the power while we're still doing maintenance. Another concept is adopting a inspection-dependent maintenance protocol where we only perform services when the condition of that component indicates that it's required. So by inspecting components and their cleanliness, for example, if that item doesn't need to be changed or cleaned, then we can forecast when is a better time to do that service instead of taking the time to do it there, which again just prolongs the duration of the maintenance. We can incorporate that task into our next site visit, for example, meaning that we can complete that current maintenance protocol much faster than if we were doing work that may not need to be done. Shifting away from the site maintenance, we also provide technical support engineers that help our customers troubleshoot any technical and operational issues. So even when we're not at site, our customers have access to a team that can help diagnose issues and can provide very fast response with actionable advice to get the system back up and running, again, even if we're not there handling a maintenance. Another service we provide is training. So operating an energy storage system is no small task. And through Wärtsilä Training Services, we provide our customers and their operators a very high degree of confidence that they are able to operate the system effectively and to manage the system and the software themselves. So they become much more self-sufficient and are able to resolve issues and make decisions quickly, although we do always provide support via the technical support channel. Now, the system's already installed. Neha spoke about a new product design that we have, but what if you already have an older generation product installed at your facility? So investigating new product solutions to retrofit is always an option. So if there is, for example, a component that maybe has a shorter maintenance duration, maybe it requires less maintenance, there could be an argument to retrofit that component into the quantum enclosure or the ACC-DCC cabinet, for example, if again, it will help us now reduce that downtime because of its differing maintenance protocol, for example. So these are just two ways from a hardware perspective now that we talk about maximizing system performance. So that really has two facets. We have reducing costs through maintenance and new products, new design, but there's also another component where we talk about maximizing our customers' revenue. So reducing costs and maximizing revenue. And we have a couple of case studies that we wanted to share with you for US customers, specifically through the use of our Greensmith Energy Management System software, or GEMS. So by using the software to support in our customers' operations, this is where the gains in the revenue really play a part. So I have 3 cases here, again, all USA based, that I wanted to walk through with you. So in ERCOT, our GEM software manages some of the largest battery systems in the world. And these projects are delivering fast frequency response. They're ensuring grid resilience during extreme weather events like we've seen the last few years in Texas. So during those periods of high demand, they're also leveraging advanced machine learning that's optimizing the energy. So these sites in ERCOT have earned over 50% of their revenue from energy arbitrage. They're benefiting from market volatility and those price spikes. And the sites I'm talking about specifically were in the top 5 earning battery energy storage systems in June of this year when you look at it on a per kilowatt basis. So this is a very strong case about software and the energy management system managing the assets. Next, we move to PJM, where one of our customers is helping the city of Martinsville, Virginia, save approximately $1 million annually through the use of a Wärtsilä Energy Storage System, where we're helping reduce peak demand and we're optimizing energy usage. And lastly, I will touch on some multi-state projects with another partner of ours, where the grid modernization is actually occurring through the use of the energy storage system. So a few facilities in North Carolina and Indiana are kind of part of this modernization. And there, our GEM software is managing and optimizing these facilities. So they don't have to be in the same state. They don't have to be in the same market. So these facilities are providing backup power, energy dispatch. They're integrating solar assets that this customer already had. And GEMS is really adding value through real-time data analytics, revenue stacking, and enhancing grid resilience. So these projects really highlight how our GEMS platform helps our customers optimize energy usage while also reinforcing Wärtsilä's role in enabling a more flexible and reliable energy future.
Wow. Thanks, guys. That was amazing insight. I hope everyone on the call thought the same. Now we're going to jump into our Q&As. So please utilize the Q&A chat box. We'll take up the remainder of the time to answer some of your guys' questions. All right, so we have a few questions already in the chat. First question is a question for our hardware manager, Neha. Is our system modular, and what is the energy capacity of the system?
Yeah, thanks for asking. So we've got a number of products in our product portfolio, but I specifically mentioned our latest announcement, which is our AC block product. So I'll focus on that one. An integral element of AC blocks is that it is inherently modular. You are now putting string inverters inside of your unit, and that means that your inverter size is the size of essentially a switchgear in our system. And so that allows you to repair and replace units a lot more easily, handle failures a lot more easily, and addresses that concern I brought up earlier, which is how modular design can increase the availability of your system. And the total megawatt hours of that system is 5 megawatt hours per BESS enclosure.
Great, thank you. Another question we have is for Ruchi. What is the percentage of loss when energy storage is injected into the grid?
Yeah, good question. So for our system, our round trip efficiency is about 98%, but losses at the AC, port really depend on other systems outside of our own as well. And so it's going to differ project to project.
Great. All right, another question we have is for Neha. How keen are Wärtsilä in terms of embracing innovation with potential partners?
Yeah, I mean, obviously, we are always looking for opportunities to collaborate with partners, especially on areas of innovation, whether that is with our battery technologies or the integrating systems that support those batteries. So we already are working with a number of partners, all focused on kind of decarbonization as a goal, and we'll continue to look for partners and opportunities to build those collaborations and seek opportunities for innovation.
Great. All right, it looks like another question is for Alicia. How old is Wärtsilä's longest running BESS project?
No, good question. So we have some of our oldest energy storage sites came online as early as 2012 under the Greensmith regime. So Wärtsilä acquired a startup energy storage company called Greensmith. So they were definitely pioneers in the space, having projects online that early as 2012.
Great. There's another question in here for Ruchi. Do you perform automation for the battery calibration and equalization process?
Yes, we do. That's sort of the what I described in terms of our automation to support state of charge calibration and cell balancing. We do perform that and offer that today.
Great. Looks like there's another question for Neha. Do the U.S. economic sanctions on certain countries impact Wärtsilä's business in the United States, as well as supply chain hurdles and increased costs?
Yeah, absolutely. So this is a big question. We could probably spend a whole webinar talking about this alone. But the U.S. in particular, when we talk about economic sanctions, right now in the current climate, we're talking largely about within energy storage, concerns about supply coming out of China. And so there are a couple of concerns that we've seen related to either certain suppliers or to cybersecurity. And then, of course, to tariffs, to the trade policies that are growing in the battery space. And so on the side of tariffs, diversifying supply chains is always an important thing to do. That means taking supply of cells to alternative countries and considering opportunities to leverage raw material availability outside of China. That being said, there's a reason why majority of supply comes out of China today. They are leagues ahead in some respects in terms of cell technology and innovation. And a lot of these trade policies are largely in response to that in the US. The other element of this is cybersecurity. So we're usually talking about our BMS, and we have taken steps toward producing and designing our own BMS internally. A lot of others have done the same to address these concerns. And that's something that we can separate out from our cell development and alleviate some of those concerns. So absolutely huge concern and huge impact to our system. We actually have said recently that policy drives this industry today, sometimes more than the technology can. And so paying attention to what those responses are and how we can minimize risk to our US customers is an important part of how we structure our supply chain and our design and development.
Great. That's very informational. I love it. There's another question here. I think it's for Ruchi. What does GEM stand for, and is it exclusive in working with Wärtsilä batteries only, or is it used with other products?
GEM stands for Greensmith Energy Management System. So Wärtsilä acquired Greensmith Energy. Oh, I can't remember the exact year. Probably Alicia or Kirsten remember. It was acquired so Greensmith Energy was acquired by Wärtsilä, and one of the main products that Greensmith Energy built was their EMS, which was the Greensmith Energy Management System, which is GEMS. So that's where the name comes from. But now, the GEMS acronym has generally stuck. We're really proud to offer the GEMS energy management system with our Wärtsilä batteries. In terms of other products, I think that if anyone has specific questions about specific products, they can reach out to our marketing team and we can get back to you with a specific answer. In terms of the question of whether or not GEMS can support other types of assets, Yes, so we do optimize storage assets, but then we also optimize storage plus renewables, including solar and wind. And we also can operate engine power plants as well. So we can run a fully islanded grid and automate that whole system, including the engine power plants, the solar and the wind and the batteries.
Okay. Nice. Thank you, Ruchi. There is another question here for you, Ruchi, as well. What generation asset other than solar does Wärtsilä hybridize with battery storage?
Right. So wind would be the main other renewable asset, as well as the engine power plants as the non-renewable asset.
Got it. Neha, can you please describe what the BESS fire protection system is, like how it differs from other solutions?
Yeah, so there are a number of fire safety systems that you can implement in your BESS enclosure. There are two primary concerns when you're thinking about BESS fires. The first is explosion prevention. So when a thermal runaway event occurs, the off-gassing of the battery modules can lead to gas buildup in your enclosure. And if you're unable to vent that, you develop an explosion risk of your enclosure. So minimizing and mitigating that explosion risk is the first part. The second part is fire propagation. You want to ideally eliminate the fire if you can, but if you are unable to eliminate the fire within the enclosure, your main concern is ensuring that it does not propagate to adjacent enclosures. And so there are a couple ways to do that with applying certain standards can be really helpful. So NFPA 855 is the reigning standard globally for fire safety, and it has two callouts for explosion prevention. NFPA 68 is explosion. What is the word? It's for deflagration. So it's reaction to an explosion potential, where when you have a certain amount of PSI that builds up within your enclosure, these panels it's passive prevention is what I meant to say. So it passively deflagrates and minimizes the amount of explosion risk within your enclosure. The second element of that is NFPA 69, which is active ventilation. And so it's ventings that are attached to sensors within your enclosure that sense gas and can vent in the event of gas buildup. The things that differ within our Wärtsilä enclosures, we are constantly paying attention to not just what the current standards are, but what future standards are coming down the line. And so we consider what is being proposed in the next iteration of NFPA 855, or what AHJs globally are looking for when they consider these systems. And we consider that when we're doing our design development, so that we're not just meeting today's requirements, but tomorrow's requirements as well. The other thing that we do is worst case fire testing. So UL 9540A is a fire test that is required globally, but large scale fire testing and bespoke testing is something that we additionally do on top of that to really understand what the worst case fire event looks like and how our system will respond. And that's incredibly important information for us to both understand our hardware, but also for us to communicate to AHJs and communities on how fires truly look when you're operating these systems.
Great. Yeah, I know it's a big part of our safety standards is with fire protection. So that's awesome. Ruchi, even with a string inverter
Teresa, do you want to hop on and ask Kirsten's question?
Sure. Can you hear me? Okay, so the question was, even with a string inverter at rack level, do you still have an imbalance at a module and cell level? And then how does Wärtsilä address this?
Right. So it's a good question, right? So the question is that, we're controlling these systems at the string level, right, with the string inverters. But we cannot control we cannot control the system at the cell level or the module level. So you may see, so you may see, while you reduce imbalance and you increase energy capacity by operating at a string level, you still can see imbalance in cells and imbalance in modules. And that's true. In general, the battery management system is designed to see those cell imbalance, and it will engage in cell balancing as well as state of charge calibration when you take that string to the designated voltage point, which is out of the 20 to 90% state of charge range, and you rest it for an adequate amount of time. Again, this really depends on the cell type of the battery, so it really depends on the specifics of that battery's chemistry. But in general, that is what battery management systems are designed to do. We continue to innovate in the field in terms of looking at next generation types of storage opportunities, as well as improving our battery analytics so that we can do things to more discreetly determine where we see cell and module imbalances so that we can, help our life cycle teams adequately manage the plants to increase usable energy. So overall, we believe that string inverters can help you improve imbalance, and that, we're going to continue to see technologies evolve that allow us to handle imbalance at more granular levels in the future.
Okay, and sorry for my technical difficulties. Hopefully you can hear me now. So Ruchi, how do we manage and optimize the real-time power market? And if you can elaborate on that concept and the system and software solutions.
Right. So we've been talking largely about our GEMS power plant controller in this presentation. We would have to do another presentation to discuss our GEMS IntelliBidder, which is our bidding platform that optimizes for market participation. But just briefly, we do have our own bidding software product. It is called GEMS IntelliBidder, and it is currently available in Australia. So if you have a project in Australia and are interested in working with us, please do get in touch with our marketing team. But we do both forecast and optimize for the Australian market, including both the energy and ancillary services markets. And we're happy to have a longer discussion with anyone who's interested.
Awesome. Thanks, Ruchi. There is another question in here, I believe, from Neha. Do you work with advanced lead carbon batteries? Lead?
Yeah, lead carbon. So yeah, absolutely. So we are constantly looking for alternative chemistries that may have their space within the energy storage market. Right now, lithium ion and specifically LFP, lithium iron phosphate, is the predominant battery technology. But we know that there is space in the market for alternatives. And there are a couple use cases that we're really looking for, the biggest one being long duration storage. Lithium ion batteries tend to have incredible performance and cost efficiency up till about 10 hours. And then after that, alternative chemistries are really starting to be explored to fill that gap and potentially come in at a higher performance and lower cost than lithium ion can do. So I don't personally have a lot of experience with lead carbon specifically, but we are always exploring alternative chemistries and where we can potentially leverage their benefits over lithium ion.
And what are the markets or countries where you see more opportunities for fast growth of BESS in the coming years?
Yeah, that's a great question. So there are a number of markets that have historically kind of always been or have built up as the main centers of energy storage. That's parts of the US, Australia, UK, but we're seeing a lot of growth in a lot of different parts of the world. Across Europe is a big one. So in the Belgium, Netherlands regions, in South Europe as well. Chile and Brazil are building up as big markets. We're seeing parts of Africa and parts of East Asia also building up. And so there's a lot of opportunity. Each of these markets have their own independent requirements and values. And there's an opportunity kind of for unique technologies and applications in each of these areas. So strategically understanding what each of these markets are and who we can best cater to is a really important part of designing our hardware and operating our sales strategy.
Great. And then I know you talked about fire safety a few questions back. So there's another question in here that's asking, and I don't know if it's related or if it's going to be separate, but does the energy storage system need electrical protections?
Yeah, so electrical safety is a big element of hardware design as well. We've seen that electrical disconnects for DC connections happen at various levels. So they can happen at the module level, the BESS enclosure level, or at the inverter side. We've kind of normalized as an industry toward having the standard DC disconnect at the inverter, but something that we have developed and keep as an option in our products is a DC disconnect at the enclosure level. And that's to just add that additional layer of electrical safety, depending on who's going to be operating these systems and how they interact with them.
Okay, great. Looks like there's another question in here for you, Neha. So when injecting energy from the energy storage system, does it have to be at the same frequency, phase, and voltage with the grid system?
Yeah, I mean, by the time we get to the point of injecting at the grid, yeah, it does. We need to ensure that we're matching what the grid needs and how it can receive that. A lot of the ability to do that comes from the interfaces between the batteries themselves and the injection point to the grid.
Great, thank you. Looks like there's another question here for you, Ruchi. So given
I'll jump in here. And I'm going to direct this to you, Neha. Given all the string inverters are paralleled on the same AC bus, how do you ensure a fault or failure is not propagated to other string inverters, essentially bringing down the entire system?
Yeah, I mean, the configuration of string inverters on in these systems, it's really important to have kind of those interfaces between each of those systems within the bus. I'm going to say and defer this to a larger topic, which you need to be discussed on the electrical side. I don't want to speak on that as that's not necessarily my detailed level of expertise, but it's a huge consideration, and it's something that electrically it's really important to design for and have lock points between your string inverters to prevent failure propagation.
Great. Hopefully you can hear me. I see the little green box around me now. Another question for you, Neha, is long duration battery tech likely to scale?
Yeah, absolutely. I mean, there is a huge demand for long duration storage, and any area within this industry that has a huge demand will eventually allow some technology to scale and be able to meet that demand. When we talk about long duration storage, I think we all kind of define it a little differently. So it is important to understand what we're talking about. Kind of the shorter version of long duration storage is like that 10 to 20 hour range, where we're talking about more than what lithium ion is designed to perform ideally at. But it's still a relatively short period compared to what long duration storage is, which can be anything up to seasonal storage. So months at a time. And we definitely have technologies outside of the battery space that meet those demands. Within batteries, it's something that we have not yet identified the appropriate technology to scale. And there's absolutely an opportunity for that to happen, given all of the research and investigation in this side of the field.
Great. Thank you, everyone, for all the insight, answering all the questions. I hope everyone on the webinar found it very insightful and informational. I'm going to put our website in the chat. So if you want to learn more, or if maybe your question wasn't answered, you can definitely go and research on our website. And then I just want to make a quick announcement of that. The recording and the slide deck will be shared in a few days. So keep a lookout for there. And thank you again for joining us. And we hope to see you at our next webinar. Thanks, everybody. Thanks to our speakers as well.